Okay? And there's various observational evidence that I think suggests that many, maybe even all AGN jets have helical magnetic fields, as probably many of you would think would be natural or even unavoidable. And I'm going to sort of talk about a couple of these today. Here's kind of a list. They include things like what I referred to, sort of longitudinal polarization implies transverse magnetic fields if the region is optically thin. So we get these jets where you have transverse magnetic fields essentially everywhere, even as the jet bends, which is suggestive of an overall field structure rather than a whole series of shocks, although some regions in the jet may have transverse fields due to shock, even in the presence of that. And in particular, also interknot regions of orthogonal field that don't seem to be associated with shocks, but still show this transverse field. And the two things I'm going to talk about today, hopefully I have time, are Faraday rotation gradients across the jets and some new interesting results we're getting with these, and the core circular polarizations, which may also be associated with helical fields. Okay. Now, just a quick slide to sort of make sure we're all on the same page, so to speak. Faraday rotation is a rotation of the observed plane of linear polarization that happens when the polarized wave passes through a magnetized plasma. Okay? And the key thing to understand here is that the amount of rotation is proportional to the square of the observing wavelength, so that if we have 3 or preferably even more wavelengths and we can measure the polarization angles, we can hopefully identify whether or not this effect is present. Okay? And in the case that it is present, this coefficient here, the rotation measure, depends on various physical constants, and the integral of the electron density times the line of sight component of the magnetic field in that region where the Faraday rotation is happening. And this is a key thing here. It's the dot product. So the sign of the rotation measure, the sign of the Faraday rotation, is essentially telling us about the direction of that line of sight field. And this is quite relevant for studies of helical magnetic fields, as was pointed out by Roger Blanford back in the early 90s. But this is our jet axis, and we have a sort of a helical field associated with that jet. This is very schematic, but it gets across the idea. And you imagine you're sitting there looking at this region of helical field. The field down here would be pointing at you. In the middle, it would be sort of more or less perpendicular to your line of sight, and up at the top, it would be pointing away from you. Okay? And so if we imagine the Faraday rotation associated with that line of sight magnetic field, if we had sort of free electrons running around there, the rotation measure here would be greater than 0. Here it would be about 0, and on the other side it would be less than 0. Now, this simple pattern will change a little bit depending on the angle of the jet to the line of sight and so forth, but it kind of gives a nice schematic illustration of why we get a gradient in the line of sight magnetic field, and therefore the Faraday rotation across the jet with the helical field. And these gradients are actually observed. Here are several examples, and I put sort of black arrows on just to sort of indicate the direction of the gradient, especially since there's no doubt that some of you lads are colorblind. So here's an example. We've got the contours show the radio intensity. The color distribution here shows the distribution of the Faraday rotation, and there's a nice gradient across this region of the inner jet shown by this arrow. This is a map taken from the literature. Shows a gradient like that sort of across the inner jet here. This is a very nice image made at with relatively low resolution that shows a kind of a gradient like this all along this part of the jet. It goes in this direction across the jet. And here, another example. This is a core region in the jet, and there's a nice Faraday rotation gradient across the jet. Okay. Now, if you sort of add them all up, look in the literature, and collect these Faraday rotation gradient cases that you think are reasonably firm, it adds up to nearly 30 of them, believe it or not. And so this, I think, it provides direct evidence for helical jet magnetic fields in these AGN. Now, I want to show you the latest case for two reasons. One, because it's a really, really nice example, and the other because it's connected with another property of these jets that may be related to helical fields. It's 1633 plus 382, which was actually put together in a sample of sources that we predicted should show these transverse rotation measure gradients because they have a so-called spine sheath polarization structure. This is showing you what we mean by this. If you look out in the jet, you've got this region sort of near the middle of the jet ridgeline that has polarization vectors aligned with the jet, which means perpendicular magnetic field. And then if you get to the edges here, you see the polarization vectors are perpendicular to the jet. which means a longitudinal magnetic field. And this has sometimes been explained as an effect of maybe shocks happening in the middle part of the jet and interaction with the medium enhancing the longitudinal field at the edges of the jet. But in fact, it may well be that at least some of these sources have the structure of polarization because of their magnetic fields. This is a kind of a schematic just to get across the idea. Here's your helical magnetic field, and if it's fairly tightly wound, in the central part of the jet, if you were looking at this, you see a magnetic field perpendicular to the jet, but at the edges, the magnetic field, so basically where the loop turns over, it has to go longitudinal. Okay? So in fact, it's quite possible that this type of kind of spine and sheath magnetic field structure could come about because of helical magnetic fields, and that's why we predicted that these sources should show these transverse rotation measure gradients. I have a PhD student who's just started working on this sample of objects, Andrea Reichstein, and it's very difficult to say exactly where this is going, but the first source that she looked at shows a beautiful transverse rotation measure gradient. The contours again are intensity, and the color is showing you the Faraday rotation measure, and essentially here's the core region all along the jet where we detect nice strong polarization. You've got sort of red and yellow down here, and green and blue up on top. There's a very nice gradient. So this is a suggestion that maybe these spine sheath magnetic field structures really are associated with helical fields, and you will actually find a lot of these sources to have these gradients. Now, there are a couple of unexpected results that we've got that I want to bring to your attention. Okay, one is that in a number of these sources, about 6 or so, we found cases where we find transverse Faraday rotation gradients in a couple of different regions, say in the core region and a little bit out in the jet, pointing in opposite directions. This is one example here. The jet sort of goes up north like this. The core would be someplace in here. Remember, the core is like the optically thick base of the jet, so the base of the jet is actually way down here someplace. And you can see there's a gradient in the Faraday rotation going across like this, and then the other direction up in the core, up in the jet. The same is true here. The core is up here someplace, and the jet's coming down here. The gradient in the core, the sort of innermost jet, is pointing down to the southwest. The gradient out in the jet is pointing up to the north. Actually, northwest and southeast. Okay? And there are 6 or so cases like this that we found. This is the latest case, which is quite intriguing. I think it's really quite neat from an observational point of view. This is an image we saw before. Here's the inner part of that jet showing the gradient sort of going down like this. This is based on sort of 2 to 6 centimeter VLBI observations. This is a map of the source based on 18 to 22 centimeter VLBI. The resolution is far poorer, and in fact, if you were to only look at this image, you'd be hard-pressed to say what direction the jet goes. But because we know it's the same object and it's essentially this image with far worse resolution, we know that the jet actually does go up in that direction. And here, in the sort of core region, you can see the gradient going down in roughly the same direction as this. Further out, you can pick up the reverse gradient. Okay, this is possible because these very long wavelength resolutions are very sensitive to even small Faraday rotations. Okay, now in the simplest picture that we're imagining here, the direction of this rotation measure gradient is essentially determined by the direction of rotation of the accretion disk and the direction of the longitudinal magnetic field. And it could be quite difficult to imagine how could the direction of the azimuthal field change. Okay, well, one possibility might be polarity reversals, similar to the sun. But it's difficult to imagine how those would happen, although I'll make a comment about that in a moment. Maybe toroidal oscillations of the jet that have been suggested by Mr. Kogan. That seems a bit far-fetched as well. Or another possibility is that we might be dealing with the question of where does the magnetic field close. Now, I don't want to get hung up on exactly what's meant by magnetic towers, but all I'm trying to suggest is that the magnetic field has to close someplace. And one possibility is that it goes out in the inner disk, and closes in the outer disk. And in this case, you've got roughly this type of situation. Here's meant to be the accretion disk rotating around. Field line sort of goes out, all the way up, comes back, closes in the outer disk. This whole thing gets wound up by the rotation. And that means when we consider the integration at the integral that gives us our net Faraday rotation, essentially if we've got synchrotron emission radiated by the inner part of the jet, for example, it will pass through both of these regions of helical magnetic field, which are wound up in the opposite direction, and both of those will contribute to the Faraday rotation. So in this situation, the total observed rotation measure gradient that we'll see is actually due to the sum of the Faraday rotation due to those inner and outer regions of helical magnetic field. And we can understand a change in the direction of the rotation measure gradient that we see as being a change in whether the inner or the outer helical magnetic field dominates the total observed rotation measure. And this could depend on a number of things like changes in the electron density or magnetic field in those two regions, how the electron density and magnetic field fall off with distance from the jet base and the jet axis, and the jet opening angle as function of the jet base and so forth. Essentially the jet geometry. And this is another interesting result that has just been accepted for publication in Monthly Notices. And it's a related phenomenon that's a bit different. In this object, we always see a transverse rotation measure gradient in the jet, but the direction changes with time. And again, I've put on the arrows to sort of guide your eye. You see here out in the jet, this is for 1997, the gradient is going downwards. In 2000, it's going downwards. In 2002, it's going upwards. In 2003, it's going upwards. Okay? And it's a strange result, but we do believe it's there. And more importantly, I think we were able to convince a fairly skeptical referee that it was there. And so, essentially, this could be the same sort of phenomenon where we have a change in which of those regions of helical field is dominating in time. And I just want to very, very briefly point out to you another idea that was brought to my attention just yesterday by Maxime Barkov. It's a completely different picture that may actually also be able to explain these results. This is just a very schematic picture where you imagine you have sort of a toroidal sort of accretion disk-like structure with cells of magnetic field. And if you have sort of alternating cells with different senses of rotation of magnetic field here that sort of in turn get, I guess, vector into the jet outflow, you could have alternating directions of the longitudinal magnetic field in that jet outflow as that accretion disk material sort of gets subsumed into the jets. And in that case, you actually could have a change in the direction of the colloidal field, which then gets wrapped up, and that leads to a change in the azimuthal field. So it's exciting because it's a completely different type of explanation for this.
So does it violate the causality?
Does it violate causality?
But
the time scale. Well, it can't violate causality because it happens. It's a simple answer. And I don't think it does. I don't think it does because, for example, for the time gap here is 2 years in our frame.
And the size is 10%, right?
Well, no, this is milliards seconds.
No. It's a 10%.
Oh, yes, this scale here is 10 parsec. Yes, so it's about.
So it takes more than 10 years.
Yeah, but that's in our frame.
Sorry?
It's in our frame, right? We see superluminal motion in these guys all the time.
The coordination change actually scale the same as Doppler factors?
Essentially, it depends on whether the pattern of the magnetic field is moving out at the same speed as the jet outflow, right? But if it is actually getting carried outward with the jet outflow, then you'd expect to see the same sort of superluminal speeds that you would with blobs or shocks in the jet. And so the question is exactly the same question: what kind of a Doppler factor would you need to be able to explain those types of superluminal speeds? And if it's something of the order of 20C, then that's okay.
No, but then the estimate for rotation measure should take into account all these. It's not the same. Should take into account the relativistic dimension.
The value of the exact rotation measure, yes. The direction of the gradient, no. All we're talking about here is whether the rotation measure increases in this direction or in that direction. It's the gradient in the rotation measure, not the value. Okay, now another thing that I want to talk about is a question of this so-called Poynting-Robertson battery. It's an idea that has been out for a while, about 10 years. It was first proposed by June2 and collaborators. And essentially, it's a simple enough idea in kind of sketch form. You have your rotating accretion disk, and there are charges in there. And if you imagine that those charges are absorbing photons from the central region, and then re-radiating roughly isotropically in their rest frame, that radiation will be beamed in the forward direction of their motion, in other words, in the direction of the rotation, and they will feel a reaction force and essentially be decelerated. Okay? And this force, it goes as the Thomson cross-section, which means that there's a 1 over mass squared dependence here. And that means that the force will be much greater on electrons than on protons in the disk. Remember, we're talking about the accretion disk here, so we don't think we're dealing with a relativistic plasma. And this will actually, is predicted to give rise to an electric current in the direction of rotation, essentially because of the different speeds of the electrons and protons in the disk. Okay. So here's kind of a sketchy situation here. This is the direction of disk rotation. You get an azimuthal electrical current in the disk that gives rise to an axial colloidal magnetic field with a well-defined direction relative to that rotation. Okay. And essentially, the suggestion is that this axiomagnetic field then provides the seed field that's wound up by the rotation of the disk. Okay, and you have a same sort of situation with the field going out, closing in the outer disk, but the direction of those outgoing and incoming magnetic fields are well defined. Okay, so here's a sketch of how this turns out. This omega is showing you the direction of disk rotation, as is the arrow here, so that the disk is rotating in this case around like that. The outgoing magnetic field, colloidal magnetic field, when it's wound up, gives you this orientation here, given by the arrow here. The magnetic field, when it comes back and closes in the disk, is given by the opposite direction here. Okay. And the intriguing thing here is that if you take this, and you can do this, you can just figure out how are the magnetic fields going to go in the two hemispheres for a rotation of a disk in a particular direction. And if you flip it over, like this, which is equivalent to changing the direction of rotation, however you want to look at it. The intriguing thing is that the direction of winding of the magnetic fields actually stays the same. Okay. So this is quite an amazing prediction, and it's possible to verify with observations. Because essentially, if the directions of winding of the magnetic field are the same when projected onto the sky, that means the directions of the rotation measured gradients that are associated with them are going to be the same as well. Okay? The sort of black star here is just meant to represent the base of the jet. Okay? So the sort of short stubby arrows here are the magnetic fields, and the long empty arrows are the rotation measured gradients associated with them. And essentially these rotation measured gradients, okay, due to the inner magnetic field, will always be clockwise relative to the jet base on the sky, and due to the outer magnetic fields, always counterclockwise. And I'll explain a little bit more what I mean by that in just a moment. And this is independent of the direction of the disk rotation or in which hemisphere we're viewing. Okay. Now, what we mean by this clockwise and counterclockwise on the sky. And here's an example. Here's the base of the jet down. Here's someplace. Here's the rotation measure gradient that I indicated earlier, going up like that. And if you imagine describing that as being either clockwise or counterclockwise about the jet base, this one is clockwise. Okay. Here's an example. Here's the jet base, the jet outflow. The gradient goes in that direction, and so is counterclockwise. Okay. And any of these gradients that we observe, we can actually describe in this simple way as being either clockwise or counterclockwise presented on the sky. Now, if we just take a look at all the gradients that we observe that we think look reasonably firm, and sort of add them all up and take a look, we get 21 that are clockwise projected on the sky and 13 that are counterclockwise. And anybody who tried to convince you that that was not sort of equal to each other within the statistical errors wouldn't get very far. The probability that that came about by chance, 21 or more clockwise out of the total, would be about 11%, and that's not enough to get excited about. However, when we distinguish the gradients that are detected closest to the VLBI core in parsecs from the ones that are detected further from the core in objects where gradients are detected on two different scales, we see a very different pattern. Okay, here on this plot, this is distance in parsecs where the gradients are detected, and just all the cases sort of stacked up one on top of the other. Circles are clockwise, and triangles are counterclockwise, and filled symbols are the ones that are closest into the jet base, and empty ones are ones that are further out. And essentially, once you make that distinction, you start to see that almost all the filled circles, almost all the inner gradients are clockwise, and in fact, all of the outer gradients that we find are counterclockwise. And if you sort of follow this through and try to see if this is statistically significant, if we consider those inner gradients, 21 are clockwise, 7 are counterclockwise, the probability that 21 or more came up by chance is only 0.6%. Okay? So this is a bizarre result. One way to explain it is if this pointing Robertson battery is actually operated. Maybe you guys can come up with another way to do this. Okay, and there are 6 of the 6 cases where we have these reversals in the rotation measure gradients, like this, are such that the one that's closer to the jet base is clockwise and the one further out is counterclockwise. Okay? That's not incredibly statistically significant, but if we find 3 more cases, it sure will. Okay, now, I have any time left, tiny time left. 5 minutes? I'll say just a couple words about circular polarization, because these are also results that I think it could be useful for you guys to know about. Okay. Now, we considered circular polarization produced on parsec scales by so-called Faraday conversion from linear to circular polarization in helical jet magnetic fields. And essentially in this picture, you have a helical magnetic field, and linear polarization emitted, say, at the back of the helix, passes through the jet, and is converted, a small amount of it is converted to circular polarization at the front of the helix. It depends on the pitch angle of the helix, and the helicity of the magnetic field. And one of the reasons this is interesting is that there's a hope to try to relate the sign, for example, of the circular polarization that is detected with the presence of these rotation measure gradients. We made a first attempt to do that in that paper. Okay. Now, the real result I want to point out to you is that just recently we published results of the first 43 gigahertz measurements, and those 43 gigahertz measurements were actually made simultaneously with other measurements at 15 and 22. So we've also got some first information about spectra. And a couple of interesting results from this. We have a couple of cases where it may be difficult to be absolutely sure about, but we've had some evidence for transverse structure in the circular polarization. In this case, we've got positive and negative circular polarization on either side of the inner jet. In this case, we've got positive circular polarization offset from the core at the edge of the jet. And it may be possible to sort of relate this to helical field models in terms of what pitch angle are we dealing with and what gearing angle are we dealing with. And so this, I don't have time to sort of explain these, but essentially this gives a sort of an example of a combination of pitch angle and viewing angle that would give this type of structure. This gives an example of pitch angle and viewing angle that would give that type of structure. Okay, now here's just the inevitable table you can't read. But the key point here is that the degrees of circular polarization here at 43 gigahertz can get up as high as 1 or 2%. Another interesting thing is that these degrees of circular polarization here, when we can measure them at 43 gigahertz and at the lower frequencies, are always higher at 43 gigahertz. This is completely unexpected for the sort of 2 main models that are usually considered in the literature, which is either circular polarization just associated with synchrotron radiation or associated with this Faraday conversion in a homogeneous source. But it turns out that this kind of behavior may actually come about in a very natural way if we're dealing with a Blandford-Kernagel type jet and we're looking at circular polarization near the time of those 1 seconds. Okay, it's exactly the same table, I just didn't want to have to sort of flip back. Another thing that we have that's interesting is that in a number of cases, like here, and here, and here, and here, in fact, we've got sign changes between the circular polarization observed at the lower frequencies and at 43 gigahertz. And so this is something also that we need to try to understand. Okay, and these regions, if we are dealing with a sort of a situation where we've got an inner helical magnetic field associated with a jet and an outer region of helical field, because of the different helicities, those should have different signs of circular polarization associated with them. And if we do have different regions in the jet that are dominated by those different contributions, they should have different signs of circular polarization. And so that would actually predict that you should have, for example, changes in the sign of the circular polarization as you go out along the jet. And this is sort of observed in 3C279. Here's the image. This is negative circular polarization and positive circular polarization out along the jet. But unfortunately, as intriguing as this looks, we can't exclude that this is due to a slight misalignment between the right and left intensity images. So one of the things we're investigating is how to try to do tests to sort of be able to exclude the possibility that this is just due to misalignment rather than real physics. But another thing that we could potentially be able to do is to look for cases where we see this type of structure and to try to correlate it with the presence of these rotation measure gradient reversals. Because if we see that there's a tendency for the two to occur together, that will make it look much more like real physics and less like misalignment. Okay, so here's my summary. There's evidence that many, maybe even all AGN jets have helical magnetic fields that could come about naturally by the rotation of the central black hole and the jet outflow. And something I want to just mention here in connection with what Alan talked about is that it appears that we're seeing these magnetic field structures, helical magnetic field structures, much further out than one would expect in the sort of picture that he presented, and we need to understand why that's true. That means that the jets are fundamentally electromagnetic structures, and that the launching mechanism is almost certainly electromagnetic, which I think few of you would probably doubt. It also, of course, means that the jets carry current, and that has implications for collimation. Okay. We've got direct evidence for, I've called them magnetic tower type models, but don't get hung up on that. Essentially models in which the magnetic field sort of goes out in the inner part, from the inner part of the accretion disk and closes in the outer part of the accretion disk. Then the whole thing gets wound up. Okay. We've also got evidence for this Poynting-Robertson battery, and in particular an axis of clockwise over counterclockwise transverse Faraday rotation gradients projected onto the sky that is consistent with the sort of inner region of helical field dominating on smaller scales. And something to keep in mind is that if this Poynting-Robertson battery is actually operating in these sources and these fields are getting carried out with the jet outflow, these are ultimately the fields that will seed intergalactic space and then get incorporated into galaxies when they form, other galaxies when they form. In terms of the circular polarization, we've got the first 43 gigahertz measurements, which were made simultaneously also with 22 and 15 gigahertz measurements. We see evidence for a transverse circular polarization structure that could also be consistent with the idea that the circular polarization is generated in a helical magnetic field. The degree of circular polarization is higher at 43 gigahertz than at the lower frequencies, which may be due to the intrinsic inhomogeneity of the jet. And we see evidence for changes in the core circular polarization sign with frequency and during outburst, and also tentative evidence for changes in the sign of the circular polarization along the jet. And searches for correlated rotation measure gradient and circular polarization sign reversals along the jet could potentially form a powerful diagnostic for these types of models. This one, not the most serious slide, but a quick fun one. I know this doesn't have anything to do with helical fields except that it's my cat.
Time for questions.
Yesterday we were talking about this helical magnetic field if the magnetic flux is not too high, and your answer would be that the magnetic field lines close somewhere close, right?
Yeah.
So this is in principle quadruple configuration of the magnetic field. And my question is that that implies that Faraday rotation gradient should be opposite for the jet and counterjet. So any observational possibilities for measuring this on the counterjet?
It would be wonderful to do this. You're absolutely
And it's
right.
absolutely not possible?
No, it's certainly worth trying, but the main problem is that it's very difficult to see the counterjets on the VLBI scales. And when you get out into the VLA scales, you're far away from the center, and the magnetic fields have gone down, and the electron densities have gone down, and it's harder to detect the effect. But I think I think there's a project there for somebody to go through some VLA archive data and actually specifically look for this effect. Because if
Because
you
I
can find
remember
even 2 or 3 sources where you could realistically do this, if there's a pattern there, it should start showing up.
And there are for sure few radio galaxies with the counterjet on VLBI scales.
Yeah, and
Like
the-
even in M87 we
there are
see a
radio
little bit,
galaxies,
right?
but they have very weak polarization.
Yeah, yeah.
You've got to be able to not just detect polarization, but detect it at 3 or more wavelengths.
And the weak jets too.
And there are weak jets too.
Yeah, is there any way to estimate the strength or the energy density in the magnetic field with respect to this, like the kinetic energy density?
It depends on the model you're dealing with. But for example, Kontopoulos and collaborators in the context of this Poynting-Robertson battery determined that essentially, I think that the sort of energy balance, the energy basically balances out. You could provide the energy in the lobes basically from the energy accreted and then due to the rotation and sent down along the jets.
Are you saying it's close to equipartition with that?
That's okay, that's a different question. I'm saying that there seems to be a match between the amount of energy that can be provided by accretion and the amount that's needed to power the lobes. Now, another completely different issue is that I actually have a student working on trying to estimate magnetic fields on the parsec scales. And he actually is finding quite a bit of evidence that lots of these objects are in equipartition. The fields are actually equipartition fields.
Fields are in equipartition with the kinetic energy of the jet.
It has to do with actually modeling how the magnetic fields are falling off with distance along the jet in a blend for kernel type model. And if essentially the radial dependence that we're finding for magnetic fields is consistent with equipartition. With a that's a good question. Equipartition with would you, Alan? Equipartition with the bulk kinetic, not the bulk kinetic energy, the kinetic
You
energy.
mean observationally or theoretically?
No, when you're talking about equipartition,
Yeah.
magnetic fields, say in parsec scale jets, you're talking about with the bulk kinetic energy of the jet or with the,
Usually they're talking about with the particles, yeah, with the
Yeah.
equipartition with the protons and electrons in the jet.
which is
But
different.
the magnetic launching models say that you should have equipartition with the bulk
Yeah.
kinetic energy.
Yeah. But I think what we're actually detecting is equipartition sort of with the kinetic energy in the particles rather than the bulk kinetic energy.
Right, but so that doesn't yet mean that they're magnetically dominated. The jets.
Not at that distance.
No.
Not at that distance. They should be magnetically dominated closer in, and further up, and if they're not magnetically dominated.
In fact,
Another question. It's possible, I think, for superluminal components, for some combination of angle of the line of sight and velocity to be seen from behind.
Yeah, that's right.
The photons
That's
coming
quite right.
from the solar. So can it produce an apparent reversal of the magnetic configuration? If you
yes,
it
in
happens to
fact,
change?
yeah, in fact. Now, if I understand your question right, you're essentially thinking, could you get something like this because of,
No.
yeah. In principle, yes, you could. And in fact, one of the things that we've also been doing is looking at the Faraday rotation happening in the core components in different frequency ranges, which we think are probing different scales. And sometimes you see changes in the sign of the sort of core Faraday rotation. Say when you look at the very highest frequencies and then a little bit lower and then a little bit lower. And one way to understand that is if we're looking fairly close to an angle of 1 over gamma to the jet axis, where gamma is the Lorentz factor, essentially a little bit of wiggling brings us on one side to the other side of that line. But I don't think that's incredibly likely to be happening here because we do see this pattern that the inner ones all seem to be clockwise and the outer ones all counterclockwise. It's a bit strange.
Questions?